Hey everyone. Last time we left off, we were looking at various examples of rings, and I want to continue and do a few more examples of rings that are going to come up in this class. So let's see. Here's one. You can just check the details on this. So if n is a natural number, then you can think of nz, right? That's the multiples of n. This is a ring, right? So this is a ring under the usual operations. Right? Multiples of n, you can add them, you can multiply them, you're going to get a multiple of n in each of those cases, and so you can verify go through all the axioms. Next example. So we already know this, so we know that Zn is an abelian group under the operation a plus b equals a plus b mod n. Now it turns out, so for so we define define AB, A times B, equal to AB mod n. Now, there's some work to do. I don't want to show it right away, but we will show it later on. So for now, we accept that Zn is a ring under these operations. It's a little bit tedious to check the distributive properties when you're dealing with mod n. So we'll prove this later on. For now, we're just going to accept that this actually is a ring, where we do addition a plus b mod n and multiplication will be a times b mod n. Next example, so given rings, let's say R1, R2, up through R sub n, define the operations on, so we're going to look at the Cartesian product, R1, R2, cross dot dot dot, cross R sub n, by, we're going to do exactly what we did with groups, right? Forming the direct product. So we'll have, say, little r1, little r2, dot, 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 up to r sub n, plus, let's say s1, s2, dot, 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 up to s sub n. That's going to be equal to, sorry, I ran out of space here, r1 plus s1, comma, r2 plus s2, dot, 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 rn plus s sub n, where that plus right there means the additive operation in the ring R1, whatever that happens to be. And then the next plus right there, so this is in R1, the next one's happening in R2, all the way down to Rn. Right? And we know that this actually gives us the structure of an abelian group when it comes to the addition. We're going to do the same thing with multiplication. So we'll say and, if we want to multiply R1 dot 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 Rn times S1 dot 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 Sn, that will be the obvious thing, R1 S1, comma, dot dot dot, R sub n s sub n, where now what do we mean right here? We mean multiplication in R1. So this is in R1. The next one would be in R2 times S2. That's happening in R2. And then this last one, that's happening in R sub n. Right? And you can check. So let's say check. Check that this gives R1 cross dot 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 R sub n structure of a ring. Now, and we already know this is an abelian group under the additive operation, so the only thing you'd have to check associativity of multiplication. That would be fairly easy because you have associativity in each of the RI's, capital RI's, and then you need to check the distributive property, so you just have to grind that out. All right, this next example, extremely important example. This is going to be one of the major topics of study in this quarter. All right, so maybe the most important example of a ring, or at least definitely one of the most important examples of ring. That's not the integers or Zn, one of those. So if R is a ring, let R square bracket X denote the set of all polynomials with coefficients in R and variable or indeterminate little x. Right, so we're going to define, let me just write down, so here, of course, we all know what a polynomial looks like. A0 plus A1x plus dot 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 plus A sub n x to the n, right, where each of the A sub i's lives in capital R, right? That's what we call a polynomial. Take all such expressions like this, and we have R bracket X. Now here, we're used to polynomials where the coefficients are in real numbers. Maybe we restrict to the rational numbers or the integers, right? But now what we see is that anytime we have a ring, we can form this new object right here, R bracket X, consisting of all polynomials where the coefficients come from that ring. In particular, capital R could be the set of matrices, right? It could be M sub n, in which case, right, we would have polynomials where the coefficients are each matrices, right? And that will make perfect sense when it comes to, as a set, at least this makes perfect sense. And then what we want to do is define operations, and we're going to define operations in the obvious way. So define addition and multiplication of, or let's say in R bracket X in the usual way. Right, we know how to add polynomials, we know how to multiply polynomials. Right, you just do that generalization of FOIL for the multiplication. And it turns out that this gives us the structure of a ring. So R bracket X is a ring. So we will see later on that R bracket X is a ring. I will go through all the details. It's a bit torturous to do, and when we get to the first chapter where we're studying rings, polynomial rings in general, I'll go through all the details. For now, we'll just accept, right, that this really is a ring. It's not difficult, it just takes some work to actually grind out, especially the, the distributive properties. So let's see. So I mean, here's just an example. Let's say, rather than actually writing down the general formula for multiplication of two polynomials, we already know how to do this. So let's look at, let's consider z sub 4 bracket x. We know that z4, I don't know why I said z4, z sub 4. z4 is a ring, so we can create the ring of polynomials z4x. And so, for example, look at this polynomial. So 1 plus 2x plus 3x squared, right? That's a polynomial in Z4 bracket x. And then let's multiply by 2 plus 2x. Okay, so now when we do the operation, I'm going to do FOIL as you usually would. But we have to remember that the coefficients live in Z4. So when I do multiplication, I'm going to do multiplication mod 4. So this is going to give me a 2 plus 2x plus 4x, which is 0, plus 4x squared, which is 0, plus 6x squared, which is the same as 2x squared, plus 6x cubed, which is the same as 2x cubed. So what we need to do is do FOIL, but reduce coefficients mod 4. Same thing with addition, right? So, I mean, I guess if I did plus, what would happen here? So we'll say and. If I do 1 plus 2x plus 3x squared plus 2 plus 2x, let's see what we get here. So let's see, I'm going to have 1 plus 2, right, that's 3. Then I'm going to have 2x plus 2x, that'll give me 4x's, which is 0x. Then I'm going to have, oh yeah, so then I'll have plus 3x squared. All right, so add and multiply polynomials as you normally would, right? But then make sure to perform the operations within, or use whatever operation is effective in the corresponding coefficient ring. There's some standard ring notation that I want to go over now. So let's let capital R be a ring. Right, now of course then our addition is going to be denoted with a plus, multiplication will be denoted with juxtapositions. I'll say that even though we already know this. So with addition denoted by the symbol plus, and multiplication denoted by juxtaposition. Now, some standard notation, the additive identity. In R. Now, what do I mean by the additive identity? That is the identity with respect to plus in the group R comma plus. So let me just say that in parentheses. So that is the identity in the abelian group R with respect to addition is denoted by the symbol 0, right? So when we're working abstractly in a ring, capital R, the identity, the additive identity, right? We use the symbol 0. That does not mean the number 0, right? It's the symbol 0, and it stands for the additive identity. The additive inverse of, say, some element R in capital R is denoted as you'd expect with a minus R. For some natural number n, let n dot r equal, well, what this is going to mean is r plus dot 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 plus r, right? So we would have n terms here, right? So when I write n dot r, it does not mean n times r. In fact, I mean, r is not necessarily a number. So n times r may make absolutely no sense, right? So this is just notation. When you see this, n dot r, it's just telling us take r and add it to itself n times. Yeah, so I mean, in fact, let me just write this note here. So I'll just say note, n dot r does not necessarily mean n times r in the ring setting, right? Because n, this natural number, might not be an element of capital R. You can say as n may not be an element of capital R. Right, so it's just notation. If we take a negative integer, so for let's say an integer, so for n in z with n less than 0, we let n dot r. Now what this means is negative r plus dot 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 plus negative r, and now the number of terms here, well, n is a negative number, so it'll be absolute value of n number of terms, right? So what it means is take the additive inverse of r and add it to itself n times. Oh, okay, and then one last piece. So for the integer r, now I got to be a little bit careful because so for the integer, I just said r, I meant 0. For the integer 0, let 0 dot r equals 0, where here this is the integer and this is the additive identity in capital R. All right, so this is just notation. When we see 0 dot r, right, that is going to equal the additive identity in R. What time we got? Oh, we're good. Okay, so let's prove something now. This will be our first theorem. So theorem 18.1. Just some basic facts about how arithmetic works in a ring. So let's let R be a ring. And let's take a couple of elements, say R and S, in capital R. 3 parts of this theorem. So the first part, 0r equals r0, which equals 0. And now this takes a little bit of interpretation here. When I write this, and we need to understand this from context, what's going on here. When I write 0 times r, what do I mean? I don't mean the number 0 times r. I mean the additive identity in r times the element little r. And what do I mean over here? This is the additive identity in capital R. So, I mean, this should make sense from being familiar with multiplying, say, integers, right? The number 0 is the additive identity in the integers, and if you do 0 times any other integer, you get 0, right? This is saying that that generalization works or is true, right? That property generalizes to arbitrary rings. Part B, R times minus S equals minus R times S, which equals minus RS. Okay, fine. I mean, this looks like, of course, this should work. Well, yeah, it works if we're dealing with real numbers or integers or whatever. But now, what we need to do is think about what this is saying, right? These are not necessarily numbers. Oops, I just stepped out of shot there. These are not necessarily numbers. Ring element times the additive inverse of some other ring element gives us the additive inverse of their product. Right? That's the way you want to interpret it. What it's telling us is that arithmetic works just like it should, or the way we'd expect it to work. And then the last one here. If we do negative R times negative S, that's equal to R times S. Okay, so I mean that's our usual way of doing arithmetic, right? If you have two negatives, they cancel each other out. It turns out that this works in a general ring, but we actually need to verify this fact. Okay, so for proof of part A goes like this. So let's look at, I'm going to do the left-hand side, 0R equals 0. So 0R is equal to 0 plus 0 times R, right? So what I'm doing is I'm using the fact that 0 is equal to 0 plus 0. Now I have the distributive property. This is equal to 0R plus 0R. Now, we're working in an abelian group, right? R plus is an abelian group. And so I have cancellation. So if I apply cancellation, what we get, so essentially I can cancel a factor from each side here, and then what I get is the identity, the additive identity, is equal to 0R. Right, so what I showed is that this thing here is equal to this thing. The proof that this is equal to this is similar, so we can say similarly. 0 is equal to R times 0. Okay, now for part B, all right, let's think about what I'm supposed to show here. And forget the middle part. I'm going to show that the left-hand side is equal to the right-hand side, and then a similar proof would show that the middle is equal to the right-hand side. So I want to show that R times minus S is equal to minus RS. Now, what does that even mean? What it means is that R times minus S is the additive inverse of RS, which means that if I take R times minus S and add it to RS, I need to get 0. So let's check and let's see if that actually works. Show that that actually works. Okay, so I'm going to do R times minus S plus R times S. If I get 0, then I can conclude that this element right here is the additive inverse of this element right here. And the way we'll do that is we'll say, oh, well, we have the distributive property, and so I can put this as R times minus S plus S, which we know is R times 0, which we know is 0 from part A. Right? So from here to here, I use the distributive property. From here to here, I just use the fact that minus S plus S is 0. And then part A tells us that R0 is equal to 0. Therefore, this object here, when added to this, gives us 0, which means that this thing is the inverse of this thing. So therefore, r times minus s is equal to the inverse of rs. And then similarly, what's the other one? So minus rs, minus r times s equals negative rs. Okay, now for the last piece. Okay. So what do I need to do? So I need to show that these two things are equal. I'm going to erase it in just a second, but yeah. Okay. So let's part C. Let's start off by looking at minus r times minus s, and this is equal to minus r times minus s. Whoa, what just happened here? Oops. Minus s. Well, okay, so what just happened? What am I using? I'm using part B. Part B says that minus r times whatever this thing is the additive inverse of r times that thing. All right, so this is from part B. And then I'm going to do it again. This is equal to minus r times s, right? Once again, this is part B. And now, who is the inverse of the inverse? Well, that's equal to rs. Yeah, so this is the inverse of the inverse of rs. Okay, so that completes the proof of part C. And so what we know now is that in a ring, some of the standard operations, the sort of arithmetic operations that we do in working with the integers or the real numbers or whichever familiar ring we are or have worked with, actually holds in an abstract ring. Okay, next definition. Let's take a couple of rings now. So let's let R and S be rings. A ring homomorphism is a function, say phi, from R to S. So I'm going to finish this sentence in just a second, but let's remember now, in group theory, what was a homomorphism? It was a function that respected the operation. Now we're working with rings, right, which has two operations, and so a homomorphism needs to be a function that respects both operations, right? So is a function phi from R to S such that for all, say, R and R hat in capital R, two properties hold. First, phi of R plus R hat is equal to phi of R plus phi of R hat. And the second property, phi of R times R hat is equal to phi of R times phi of R hat. And remember, of course, just as with groups, right, that plus means addition in R, that plus means addition in S. That multiplication means multiplication in R, this multiplication right here means multiplication in S, right? And so when this when these properties hold, right? We've got what we call a ring homomorphism. Most of the time, I'm going to drop the word R. If it's clear that we're working with rings, I'm going to say the word homomorphism, and it's understood that it's a homomorphism of rings. And we learned some properties of homomorphisms when it came to groups, right? Many of those properties carry over to the ring setting. So let's say many of the techniques and properties of group homomorphisms, well, let's say many of the techniques and properties, how do I want to say this? Properties of ring homomorphisms are analogous to those of group homomorphisms. And so in certain cases, when we have a theorem that involves ring homomorphisms, I'll say the proof is similar. This is basically the same proof that we did when we were working with groups. For example, there's a first isomorphism theorem. There won't be a whole lot to prove because there's a whole, because most of it we've already done back when we were studying groups. Another definition. If phi from R to S is a homomorphism, yes, ring homomorphism, right? R and S are rings. The kernel of phi is the set kernel phi, and now it's going to be equal to the usual thing, but let's see, the kernel should be the set of all elements in the domain that get sent to the identity. And so what do we mean in that case then? So it's the set kernel phi, that's the set of all little r and capital R, such that phi of R equals 0. And here, what do I mean by 0? I mean the additive identity in capital S, right? If you like, you can even put a little 0 sub S if you want to be very precise. But typically, we're just going to understand from context. This 0 can only mean one thing, right? Because phi of R lives in the codomain, so it's got to be 0, the additive identity in S. This is really another little bit of terminology, although I'll say it as a definition. So a bijective homomorphism phi from ring R to S, right? This is an isomorphism. So this is called, and I'll just put in parentheses, is called a ring isomorphism. If I need to be specific, I'll say the word ring, but typically I'll just say isomorphism. In this case, we say that R is isomorphic to S, and right, I feel like your book doesn't even use a symbol for ring isomorphism. I could be wrong, but we're going to use the same symbol that we use for groups, and so and we'll write R. Right, that symbol, the same one we used when it came to groups. All right, so from an algebraic standpoint, isomorphic rings are indistinguishable. Okay? So isomorphic, that's the end of the definition right here. But just for your understanding, isomorphic rings are algebraically indistinguishable. All right, it's just like a renaming of elements. Here's an important example I want to look at. So let's let capital F be the set of all functions from the real numbers to the real numbers. And here we're not requiring that there's any structure on these functions. They're just functions, not necessarily homomorphisms or anything like that. Just the set of all functions. Under the operations, where we do little f plus little g of x equals f of x plus g of x. This is how we add functions. And here's how we multiply functions. F times g equals f of x times g of x. So under these operations, it turns out that f is a ring. Right? So f is a ring. There's some details to check. And I think that's actually going to be on your first homework assignment to actually check the details there. Now, okay, so for now we're going to accept that we've got a ring. And I want to continue with this example. So given little a in capital R, define, and we'll use the symbol phi sub a. So phi sub a of little f. Oh, let me be a little bit better here. So define phi sub a from capital F to R by phi sub a of the function little f equals little f evaluated a. So f of a. So now, if I do phi sub a of f plus g, that's going to be f f plus g of a, which equals f of a plus g of a, which is exactly phi sub a of f plus phi sub a of g. So phi sub a respects addition, and we'll see it also respects multiplication. Just crank it out. So say and phi sub a of fg equals fg of a, which equals f of a times g of a, which is phi sub a of f times phi sub a of g. So what we just showed then is that phi sub a is a ring homomorphism. So therefore, phi sub a is a ring homomorphism. And this has a name called evaluation at A. So the evaluation homomorphism, that's an important technique when it comes to ring theory. So we'll make use of this and similar type homomorphisms, evaluation type mappings, fairly regularly in this class. Hey, I'm not sure what happened. I don't know, my phone died, or the camera turned off or something like that before I got a chance to say goodbye. So I just want to say goodbye. We'll pick up right here at the end of, or after this part about the evaluation at A as the homomorphism. So we'll move on after that. Okay, so see you next time.